All right, so the purpose of what we're doing today is to look at some data using Excel so that in our lab 2, which is running as lab 1 is going on, we could take our growth or height data and compare it from the fluorescent to the LED. And just trying to show you how we're going to do this lab and make some sense of it in terms of what we've been doing in class, okay? Let's step back and try to understand what we're trying to do here, okay? So we have these fast plants growing from day 0 to 4, and again, your days will be different, but this is just an activity that will finally get finished today so that we can actually start maybe doing it live with our own data. But we had fast plants that were germinated in fluorescent light, sorry. And at day 0 to 4, this is showing that we germinated them in the fluorescent light, and we measured them day 0, day 4, and then day 6, okay? And you're gonna notice something, okay? Our LED data, this is our modified, okay, dependent or independent variable. What do we modify? To test something. We modify the dependent variable.
The independent?
The independent. You don't modify the dependent variable. Dependent variable is, again, the response of an organism. Okay, this is biology. These organisms can't speak. They only speak to us in terms of how they react to stimuli. And why would they react to stimuli? Because they have certain alleles. They have different genetic code. They have different expression. They interact with the environment a little differently. That's key here, okay? You're a different species, different organism. You have a little bit different, you have different genetic code. You have a different way that you interact. Could it be better or worse? Remember, evolution is a compromise, okay? The compromise here is that you may be good at one thing, you're bad at another. Bottom line is you survived to this date because, well, you were naturally selected for some alleles you already had in your what? In your toolkit or in some low frequency that benefited you in the future. We'll talk more, but we're talking about fast plants, just to think about this. Fast plants were artificially selected, okay, over 20 years, they picked the fastest growing what? Fastest growing fast plants to actually reproduce. It wasn't natural selection. Humans said, hey, that one grew faster, okay? This one is growing faster than this one, okay? And we're not going to what? Use its genome to reproduce. We're gonna pick only the plants, and these are leaves, right? Pretty leaves, okay? We're only gonna let these plants here reproduce with themselves, and we're gonna leave these guys out. It's as if, okay, nature was selecting these guys only. And they would only do that if there was some kind of selective pressure that eliminated the smaller growing. But Dr. What was his name again? I forget, but what's his name from the Wisconsin, University of Wisconsin, only picked, it was Williams, Dr. Williams, artificially selected them by only picking, of course, the alleles with the most and fastest growing time to maturation, meaning when do they start flowering? And in fact, if you walked in today, you probably recognize that there's buds on them. A lot of differences since Friday, or for you guys, Thursday, right? Thursday? Okay, so it's a hard time to understand this remote thing. But in any case, that being said, they were artificially selected to grow in white fluorescent light. So you have to understand that these guys are good at that, very good at that. Now, what we're trying to do is we're going to see how well they grow, okay, in light-emitting diode light, LED. More specifically, it's not about LED, it's about the fact that this LED is actually a grow light. It's using red and blue parts of the spectrum only. Now you may say, oh, okay, what's white light? White light is all the spectrum, okay, so it includes the blue and the red. Now these guys are undergoing photosynthesis, and photosynthesis, we have learned, basically these plants utilize the blue and red part of the spectrum. So only showing blue and red, okay, should provide, okay, more light that the plants can utilize. But the question is, if these guys have been artificially selected to grow in white light, maybe they have adapted in a way, or we've picked what? Only the ones that had the alleles that are able to pull the blue and the red from the white the best. So what we're really doing here is not just measuring height of plants in their different colors, we're really asking the question, okay, are these alleles or these plants who are best suited after all of the artificial selection of so many generations, okay, are these guys as good, okay? Can these grab the red and blue spectrum, okay, of the light as well as, or as if all of the light was blue and red, okay? So this is going to shine a lot more blue and red than this guy does, but maybe these guys have adapted, I don't say adapted, they were artificially selected to be very, very good in the white light. Maybe they have the ability to grab as much of the blue and red spectrum. And we're going to look at this in more detail later in the year. But basically, what are we looking at? We're looking at how are they best suited for their environment. So the dependent variable, okay, we're looking at growth. Specifically, we're looking at height. Now, height has some issues. I'll agree with that. Height has some issues, okay? And we'll talk about that. But we're looking at the height of plants in centimeters. And so we're going to see if the difference of the different lights, the modified light on them, okay, provides a significant difference in how high they grow, okay? And you can relate that to health of the plant, growth of the plant, okay? And again, there are some limitations here, as there always are. So the dependent variable is the height. Height in centimeters, okay? Now, the independent variable is what? Height depends upon the type of light, okay? The type of light. Now, we're kind of interested here. I am too, the type of light. Why am I interested? I'm interested because I know that these guys have the alleles to grow really well in that white light that contains all the spectrum. This light here is completely red and blue, which is basically dialed in for exactly the light used in photosynthesis. Will it make a difference? Okay? Okay. Will this provide more of the light necessary for better growth and larger height? Okay? Or will they be the same? Will there be a significant difference? Okay? I would expect a significant difference in my hypothesis if the fast plants were not what? Artificially selected over 20 years. So maybe my hypothesis would be what? If I want to write a hypothesis, assuming the artificial selection of just picking the alleles of the fast plants that are really, really good at grabbing the white light. Remember, if these guys got to maturation faster, okay, than other plants, then we would probably suggest that they were really, really good, or they had the alleles by some genetic variation, by the sexual reproduction that occurs in plants, to pull as much red and blue out of the white light, more so than the ones that took a lot longer. We can make that assumption. That makes sense? So, given that, what would be your hypothesis? And how would I write that hypothesis? Well, for me, it's an if-then statement. To keep it simple, if the independent variable does something, the dependent variable will do something. So, given maybe, and again, there's no right or wrong way to go with this as long as it's a measurable statement. So for me, maybe I would say, if the fast plants were grown under a red-blue LED light, there'll be no statistical difference between them and the same fast plants grown in the fluorescent light. You could say, if the fast plants are grown in a red-blue LED light, they will grow taller than the fluorescent data. Both are correct. There's no wrong way. We're just making a line in the sand of how we're going to test this. For me, I'm thinking there'll be no difference. And again, our data here is made up, okay? Yours will not be, all right? So that's what we're doing. Now, how am I doing this experiment? What is my goal? My goal here is to have a graph, a data. And again, what's my line in the sand? I want to see statistical significance. So I'm after error bars. And that's where we have the standard error of the mean. And we'll get that to a graph today. So, fluorescent data, we measured 4 days. All of the plants were grown under fluorescent white light data, okay? And that's important because they were naturally selected to be germinated under that white light. We didn't want to mess with that. And then we measured them at 4 days and then 6 days, okay? On the 6th day, we split half of them, okay, into the LED grow light area, and we left half of them. So on the 8th day, the ones that were left, okay, we measured them. On the 8th day, the ones that we split after the 6th, that's 2 days, that's basically 2 days of growth in between, okay, we went to the LED layer. So understand, this is half the group, okay, after 6, we're going to split the group in half, okay? We brought half of them over to the LED. 2 days later, we measured their growth, okay? And then another 2 days, we measured another growth, okay, of LED data. What about here? Well, here's the growth of the same LEDs that were left behind. Now, what's confusing is, Mr. Grodsky, what is this right here? If you look very carefully, this is the same. Now, I'm thinking about designing a graph. And I'm going to design the graph by looking at the mean. We're going to generate the average, right? So this is going to be the mean height, HT, okay? And then we'll have 0, 4, 6, 10. So 4, 6, 10, 4, 6, I can do this, 8, 10. Now I want to do a line graph. You certainly could do many different things here, but maybe I get something like this. Okay, and then maybe for the LED, and I don't know. Now, you notice something. This will be right over the top of each other. You notice we split the LED when? When did we split them in half, the groups? Right after, right. So our lines are going to stack on each other. So I just took the same data there so that my line is stacking to show that there's going to be a splitting. Okay? Could you have started it early? Could we do it differently? Sure. All right? But I wanted to show that. Okay? And you don't see any difference here because they're the same group. It's only after day 6 did we split them. Now, the next thing I want to show is that, how do I know if there's some significance or not? Well, we're going to do standard error of the mean. Okay? And we're going to have error bars for each of these. And the error bars are going to see if there's a statistical, what? Difference with plus or minus 2 SEM, which tells us something about 95% confidence. And if I get error bars that don't overlap here, what does that mean for day 8? What does that mean for day 8? That making red, let's make red LED. And black is fluorescent. Yeah, Will?
That LED makes or allows the plants to grow faster than
Okay,
fluorescent.
you're jumping right into a conclusion. Let's just go right into results. Results is just looking at the data, and what does the data say? The conclusion is an interpretation. We'll get there. So let's just talk about what does the data speak to. What's it saying to us here if these two error bars don't overlap? Yes?
After the first 2 days, the LED lights in plants grow higher than.
There is a significant increase in height in plants that are what? That are grown in LED lights.
Yeah.
And then here there is what? Not. And okay, now, that's just looking at the data. Now, what does that mean is something you're going to have to what? Think about and interpret and try to think, we can think why the organism is doing that. It's called a leap into the organism. Okay? So, I've just made some data up. So that's our goal. And that's when having my goal in mind of how I want to present this, will affect how I lay this out. So me laying out these data tables wasn't just arbitrary, it was in a way to try to present this information, okay? But what are we after? Hey, are the alleles in the fast plants, okay, because of artificial selection, so good at pulling the red and blue out of the white light that there will be no statistical difference in their height when they're grown only in red or blue light? Or maybe for some mutation that was also artificially selected for, they can grab a wider spectrum of light. They don't need just red and blue. So maybe they've gotten so good on their white light, they can pull other spectrums of light. So this is I would think, a question, an honest question to answer. I think it's kind of interesting, okay? So that's my goal. So let's get there, okay? So let's try to fill this information in. Now, as I told you, okay, this is an activity. I don't know what the outcome's gonna be, and it's not gonna matter, but what we're trying to do here is go through the Excel spreadsheet, and then eventually we go with our lab, we're gonna put our data down here. So, what we're gonna do is you should have all this here, okay? So you should, basically all of this was given to you. I may have colored this to show that it's an LED. Did I do that or not? Okay, cool beans. Okay, so this won't take too long anymore because we keep doing it. At some point we're gonna get we're gonna get somewhat proficient at this. Okay, so I made our titles, and you can do this so many different ways, but here we go. So let's get our average together. So it's really helpful, I think, and you could do this so many different ways, to put all the data underneath here. Excel is a continuous sheet. It'll go on forever. So we're going to stack up. We're going to gather our data. You're going to add it to the Google Sheet. We're going to pull the Google Sheet as a class down here, okay? And we'll do that for all the data, even the groups that are split up now, okay? Let's pretend that happened. Okay, so first step, I'm going to click on the mean. I'm going to click on that box. That's where I want the average. Okay? So, I'm going to insert. Now, so many different ways. You can hit this insert button here. Okay? I'm going to hit the insert button on top, and I'm going to do function. Okay? Sometimes giving me too many choices is bad. So, I'm going to click on the top, insert function, and at some point, no matter how you do it, you're going to get this box comes up. And I'm going to hit the average, which is the mean. And I'm going to insert that function. Okay. Then we have these parentheses here. It wants to know what numbers you want to average. It's not that smart, so we want to take this entire range. Now you could type it in. I think it's sometimes just easier just to select it, okay? And again, sometimes we select other things that are not part of the right range and errors can pop up, and I've certainly done that a couple times myself, so it's not a big deal. So I'm going to select 2.3, and I'm going to try to just scroll down. Even if I over scroll, okay, to an area that doesn't have numbers, it won't count that as anything, okay? And I'm going to hit done, I think. Okay, so I made a mistake already. And I'm going to start from scratch. Someone's yelling at me. Okay, so I'm going to insert the average. And sometimes I do this wrong. Scroll. Circular reference. What am I doing here? I know I deleted mine, so I don't know. That won't let me. Christmas. Hold on. Do this again. So, average. Insert function. Seems like when I select it right, it gives me the right value here. And I'm no expert, but I know I can get through this. Let me hit done. And I got 2.69. Are we there? Okay. I was holding you up, sorry. All right, we good? We got 2.69. Okay. Next thing, standard deviation. And that's an easy one. It's standard diva. Maybe you guys are divas, but you're not like crazy diva, you're just a standard diva. So STDev or STDEV is a standard deviation. So I'm going to click on that. I'm going to insert the function. And just like you guys did with the worksheet last week, you took what? The mean, and this is minus what? Whatever. You have to take this mean and do a variance, right? But the bottom line is, we don't have to do that. We can have the spreadsheet do that for us, especially with 300 or so data points. Okay? So same thing. I'm going to select all the measurements without making a mistake, and I hit done. And somehow I have an average because I clicked the average. Bad Brodsky. Standard diva. Insert that. Okay, I can try this again. And sometimes she doesn't scroll on me. Sometimes it doesn't like me. Or I need to scroll up, I don't know. Are we good? Okay. SEM. Now this one, we do not have a nice formula for, so we're going to have to type this in, and that just shows you how powerful Excel is, because you don't need, okay, to have everything automated. You can make your own formulas, and right from the Regents reference tables, I'm sorry, for the AP reference tables, okay, boy, that's too close, but pull away. We should know, hey, it is chi-squared, by the way. Have a good time with that one. So, SEX, so we have standard error of the mean, and that's the standard deviation divided by the square root of n. Yes?
My laptop died. Do you have a charger?
I do, but I need my charger.
Oh,
Okay, cool. Mine's kind of low, too. Okay, so SEM, we're going to have to take the standard deviation, which we just did. So we need that value. So what we do is, we're going to have to type this value. So I'm going to click this, which it's easy to work either in the box or above. Okay, so what I'm going to do is I'm going to click up here and say equals. All right, so I clicked on SEM, equals. Now I need this value. I need the standard deviation. Okay, so mine is H, this number I need is H7. So what I'm going to do, whatever yours is to get the standard deviation, is equals H7. Christmas. Equals H7. Okay? So it tells me take this value and put it here. Okay. I want to divide by, so backslash. Yes?
can I switch over?
Absolutely.
All right, thank you.
Yep. So backslash. Let's divide by. Now the function in Excel, it's for a square root is squirt. SQRT. So when SQRT, and it'll probably pop up as you do it. SQRT. There it is, capitals. And SQRT, you're going to see, if you have to add the two parentheses, do that. And it wants to know the square root of what number? Okay, well, you'd have to find the actual number of plants. Okay? And since I know that I added 20 here, I'm going to put 20 in that parentheses. Careful, and I make the mistake all the time. If I was to move my cursor and hit this box, it's going to put that box in there. So you've got to just kind of click up there, and now I'm going to hit enter. Okay, and there is my SEM. Okay, now, but that's SEM just one, plus or minus, okay, the standard error of the mean, which gives you the range of what? The range of confidence that your mean is what it's supposed to be. Remember, a low SCM standard of the mean means that your value is taking on a lot of data, a lot of plants, and that your value is approaching the actual mean of the population. We don't have every fast plant ever grown in here, so there's going to be some what can I say, lack of confidence. We'll talk about that as we do this, okay? So I don't need this anymore, okay? But this SEM is plus or minus 1 standard deviation from the actual mean. We want plus or minus 2 to get the 95 percentile. We want to have 95% confidence that in that range, the actual mean is in there. We want it small, so we times this by 2. So I need the SEM, so I click that, and I say equals. And I want it equals to this value here. So it's H9, so equals H, for me it's H9, whatever it is for you. Okay. And times is just going to be asterisk. So if you do shift, I believe 8, you get that asterisk. I think they call it asterisk, right? Shift 8, you get that. That's a multiply sign in Excel. And I'm just going to put 2 there. So all that means is take the value of H9, and I got that wrong. I want H8, right? I want the value here, so I made a mistake. Times it by 2. Careful about clicking other boxes because that will come up. I'm going to put the cursor up there. And I will hit enter. Okay, there we go. Which makes sense, it's double. Now, I'm going to clean up these words, yes?
My reader has the circle that has the all colors.
Yeah, for some reason you get the circle, it's trying to, you're going to have to force quit it and open up again.
Okay.
For some reason it does that, okay? But you'll be able to catch up. So what I'm going to do is I'm going to select all these boxes. I want to format all the boxes here. I don't need this much information. As we'll learn in chemistry, is insignificant numbers, right? So I'm going to make sure that there's only 2 decimal places there. So I go to Format, Cells, and I'm going to go to Number. And just by default, they show us 2 decimal places. If I wanted more, I'd have it there, but 2 is good enough. And then I hit wherever it might be, OK or done. And you can see in all its glory that we have what? 2 decimal places. Now this is the cool part now for me. We just told this, do an average and use this data down here. Hey, do a standard deviation, use these numbers down here. Hey, let's do a standard error of the mean. We need the SD, divide by the number. We knew it was 20, square root of the number, and hey, take this number times by 2. What's kind of cool is we don't have to keep doing it. We have data for all these days below. So if you notice, it's all here. You'll do the same thing. But now what's the greatest part is, okay, is to take the mean and take this corner and now drag it over to day 10. Now you gotta click that green corner. And you drag it over, lo and behold, what it does, it says, hey, do an average, but now take the average of the numbers below. Do an average here too, but take these numbers over here. So we've automatically taken the average, or the mean, of all the data columns below. Guess what we can do with the SEM? Standard deviation. Same thing. Find a little box and drag it over. Don't drag it over 5 times because there's no data here, so you'll get some kind of error message, right? Because we have these columns here. So it's basically dragging the formatting to get this number. This one's based on over here. It's smart. It says, okay, we'll do an average and we'll just do it over here. I'll do the same thing with the SEM. And I'll do the same thing with the SEM too. Yes?
I missed the SEM part.
Okay, so what you're going to do is hit this box here. And since we need the standard deviation, because standard error of the mean is equal to the standard deviation divided by the square root of the sample size. So what you're going to do is say, find your SD. So whatever, for me it was H7. So click this box and say what? Equals whatever H, whatever value, coordinates it is for you. So I'd say equal whatever your coordinates are, H, whatever. For me it was H7. Okay, these would be different for you probably. Backslash, that's divide by. To get the square root, we use squirt capital SQRT. And then you're going to see parentheses. You're going to put 20 there because we actually had 20. Okay, when we do this with our data, we'll have to count. But we can figure it out because you'll get a starting number here and an ending number, and you can subtract. And then you're going to hit equal. I'm sorry, then you're going to just hit enter. Make sure you're doing it up here. Don't click another box, right? And so, and there it is. And so that should pop up. And then to do the plus or minus 2, which would give you 95 percentile, because that's really what? 2 standard deviations away from the true mean, okay? You take this value, so equal H for me 8, okay, here, and then I just do the asterisk times 2, which is the time set by 2. I'm just multiplying that by 2. And then all we did was drag the corner, which is really cool. One of the nice features is now you just automated that. And what's kind of cool is if you had a spreadsheet that was changing, like you could set all these things up, and as you put in the data, these things would fill, right? We don't have all the data day 10, or I don't know what day we're at, but it doesn't matter. Okay, so here we go. So now, here's what I can do over here. I'm going to take let's say Command C. I'm going to copy that. I'm going to bring this over here. Command V. All I did was select that. Command C is copy. I could have just selected this and hit edit copy, and then hit this and hit paste. Okay? Gotta be careful here though. Okay? The reason I want to be careful here is because I want to see what it's looking at. This is M. Oh, it did. Nice job. So it's looking at M12 to 31. So it's also looking for the same range. I wasn't sure if it was going to be looking for this average was based upon this. But notice, the numbers are the same, as they should be, because we designed this sheet to have what? To have the day 4 and day 6 of the fluorescent data, okay? All right, now that I know that this is looking for the M numbers, guess what? All I'm going to do now is drag across. Now, just so you know what we're doing, okay? This LED data starts out with fluorescent because we want to make a line that stays the same for a little bit and then separates. And then, so these two, day 0 to 4 and day 6, which should be exactly the same values as you have for the LED, for the fluorescent, these will be different. Okay, so all we're doing is now automating the process and dragging that little green corner over. Don't forget, we put in, or you guys will put in the data underneath here, okay? Now there has to be an adjustment here, And the adjustment is that didn't we split up half of the plants? Now, when we do this in our class, will it be half of the plants exactly? No, probably not, okay? Because the numbers will be different. Everyone had different numbers, so you're gonna have to actually find that number. So these guys are fine. It's these guys I'm gonna have to adjust the standard error of the mean, the n number. So I have to go in here and make adjustment here because it's not that smart, okay? Remember, this is mean SD SEM. I'm just gonna copy this over again because I don't have it here. Just so I remember what I'm doing with, okay? So I'm looking for SEM. I know that these guys are fine because they're based on 20. We didn't split them up, but these have less the plants. You should have. Oh, we might adjust the ones over there too. Here we have 10. We do. We'll adjust that. We'll do these first. So this is SEM square root of 20, but because we split that plants in half, that should be 10. So let's just change that number in the parentheses to 10. And if you notice, as soon as you don't click this like I wanted to, click up here, notice the number is going to change here too, because this one depends upon it, okay? Don't click, and it did. I'm going to do the same thing over here, and I probably could just drag this over, and it did, because I changed the formatting here and just dragged it over. Okay, yes?
For the fluorescent light for day 8 and 10, when you have to...
Yeah, we're going to go back. I recognize that I made this mistake. Good point. Excellent. Yeah, so because we split them up, these guys got to change too. So this is not based out of 20 anymore, it's based out of 10. So I've got to change that to 10 as well. And when you're doing this with your lab, again, it won't be that pretty of half. You're going to have to count how many. But again, all you got to do is see what the column number you start with, and when you end up at subtract and you have it. Okay, so this is 10. Okay, hit and enter, and I'm going to drag this across. All right, cool. You guys are getting, I'm going to make this smaller, not to confuse myself. Home. Okay, and because I'm OCD, I'm going to just, yeah, there we go. All right, and so there we are. And if you look at something, standard error of the mean got bigger for these groups compared to here. Why did they get bigger? Yeah, smaller sample size. And that's the problem that we're going to have in many of our labs, is that we're going to have small sample size, okay? And of course, the smaller the sample size, the harder it is to get a random sample that represents what? The entire population, right? Take my family and say we're going to use your family as a random sample of height of people in the United States. Not going to be a good study. We're going to have a big error bars, obviously. Okay? So the more data points you pick, the closer you get to the true mean.